Negative cycle means the current is coming here, right? Inside can only go through D1, right? Again, go at this direction to RL, comes back here, comes back here. Oops. Comes back here, comes up, go to D2 and comes back, right? So always the current is passing through RL is this direction, right? For both of the positive and negative cycles. And then again, we can put some capacitors to regulate the output, not varying too much, right? If you do not have the cap, the output is just like this, the dotted line. But once you put the cap, it stores the energy or the charge or the voltage. And then again, it will drops during this dead area, right? And what is the advantage over the half wave? How is the advantage comparing to the half wave rectifier? How is the ripple higher or less? It is less, right? Because for the half wave, basically you had this part, right, like this, and then that cap was charged over here, starting discharge from here all over to this cycle, right? But for this one, you see the next cycle comes in so earlier. So the cap has less time to discharge, right? So overall, with the same amount of cap, basically the discharge for this will be less than the half wave, right? So if uh we want to be more accurate sometimes, basically we also consider the let's see where is we also can also consider the basically this is the V in V out characteristic of the full wave rectifier. If we want to be more accurate, actually when the V in is changing, right, from zero, basically the in series, I mean, in each cycle, two of these diodes are in series, right? Let's say in a positive cycle, D3 and D4 are in series, right? So if we want to be more accurate, basically, once the V starting from zero, it cannot turn on both diodes until reaching 2 VDA on. So basically, it does not generate any output first. And afterward, it starts following the input, right? And also for the negative cycle. So this sometimes makes the output like there is some dead zone here. We call it the dead zone. So remember if there you hear this name of dead zone for the diode basically or the rectifier basically the turn on voltage of this, right? Okay, and other than this, basically we saw how we can make the some sort of after the full wave rectifier, we can use some sort of diodes to a little bit regulate the output voltage, right? Reduce the variation. And one more practical way, instead of adding series resistor or stacking series resistor, is using a Zener diode in the reverse bias format. So the Zener diode, if you remember, it will be breaked at the uh, reverse bias at certain voltage. They can control it and design it, for example, let's say for 5 volt, right? But in fact, once it breaks, the small signal model is pretty much similar to the normal diode, and then you can calculate it, the ripple performance, right? So here it's just describing uh, some definition for the regulators. the voltage regulators. We call it line regulation and load regulation. Just keep in mind for the regulator, these terms are showing how good the regulator is, a voltage regulator. For example, line regulation means how much V out changes once the input voltage changes. And the load regulation means how much V out changes again once the current of the load changes, right? And once you have the model for your regulator, basically, right, it will be like the small signal model of the regulator over here. And then you can basically calculate easily how much V out changes once the V in change, which will be like this, or how much V out changes once you are changing the load current, right? So just remember these terms. Maybe later in the other courses we will use it more. And we already had seen there this diode can be used as the limiter or clipping. If you series it with the bias voltage, you can control the limiting zone, right? These kind of things. And okay, there is one more basically application for this diode circuits, which is like this kind of voltage doubler. So the configuration is like this. You have this chain of the diode and caps, basically, and you have an AC source at the input. So you can see that basically once the input is a negative cycle, let's start with a negative cycle at the input. Which cap is charging? You think? Let's say starting once at the negative cycle. So let's say the input is like with this polarity, right? Means that the current suppose passing which direction? Like this direction, right? So which cap able to be charged? C1, right? Because the D1 can pass this current this direction, right? The D2 is is off, right? And then what will happen is the the C1 cap will charge with what polarity? Polarity of charge cap is like this, right? Right? Because we were charging like this direction. So the polarity of charge cap is like this. So it stores this value, let's say the peak value, right? And then, oops. And then what will happen in the next cycle or in the positive cycles? D2 can turn on and you have some initial V in voltage, right? Let's say the V peak with the same this polarity. So this V peak plus this V peak, right? Initially drops across the C2, right? But so if there was no charge sharing between C1 and C2, basically the V out would be 2 VP just suddenly. But in practice, basically the sum of the charge of C1 should in fact shared between the C1 and C2. So it is not just jumping just quickly to the 2 VP at the output. It right there is some charge sharing between the C1 and C2. So if we assume that C1 and C2 are the same value, then half of the VP charge of the C1 goes to C2, right? And what you are seeing that the output voltage basically start increasing, first of all VP, and then it keeps step by step going up. but the final value basically is 2 VP. That's why we call this voltage doubler. And if you put more of these things in series, you can make it tripler or what, 4 times or 5 times like that, right? Okay. And one more application for the diode is just to let shift the voltage level, right? Once the diode is biased, it is like a constant voltage source, right? And then you can shift the V in with some DC value to V out, right? Sometimes we use it to just adjust the DC levels, right? You bias the diode, the bias diode looks like a sing, like a voltage source, and then it just reduce the voltage as you want, right? Or here, it is showing how you are increasing basically the DC level. You can use the diode as the switch in your circuit. Let's say you want to make something like this circuit, like you want to have some control whether the V in goes to the V out or not, right? So here is showing how you can start with. You put this diode here, but this diode can pass the positive cycles of the input, right? It's not very well switched, cannot turn on at whole region. So eventually you will come up with this solution, for example. So this solution basically, once the diodes are off, then this back-to-back series diode, basically anti-series diode, basically, they cannot conduct. So it's really turned on for every input voltage. But if you somehow pass some current inside the diodes and turn them on, then this will be shorted to there, right? So it needs to make some modification to just single diode to work, right? And here also mentioning that though this thing looks off, let's say for the off region, right? Let's say you are turning off the diodes, but we know that each diode has some junction capacitor. So this is the next level of accuracy sometimes we need to face with, right? So basically you want to have an ideal switch that is off, but in fact the switch, which are these diodes, have some small junction capacitors, right? And then through this junction capacitor, it is possible that the AC signal pass, right? Because caps can pass the AC signals to the output, right? So we are seeing that depending on the accuracy and the requirement, actually, we need to add some more details or just can skip, right? So let's go to the next level of the course for what? For the transistors, starting. So any questions so far? Right. The diode was how? Was it more difficult than the... Okay. So let's start here to show another semiconductor components, which is the transistor and the bipolar transistor, right? So let's just quickly review how it works. So the bipolar transistor is consisting of 3 regions of like doped semiconductor, like N, P, and N, or P, N, and P. So it is always some sandwich of the opposite type of the semi doping between the two similar, right? So we start with the NPN transistor first. The symbol that for NPN transistor we put is like this one, right? We have one port called emitter. We have the center port called the base, the other one like collector, right? And there is some arrow here basically showing that this transistor is NPN, right? Because why the arrow is like this? Because the from the base to emitter for the NPN transistor, actually there is a diode, right? PN diode basically, right? This PN diode can conduct the current at this direction. That's why in the symbol we have this like this, right? Uh, if we go back to the single junction, basically the PN diode again. So you remember for the forward bias, which kind of carriers were conducting more? I mean the majority or the minority? You remember? So in the forward bias diode, basically this P region, the holes were conducting because this barrier voltage, the barrier region will be smaller, and then the majority of carriers will conduct, right? For the forward bias diode, right? The holes of the P and the electrons of the N was conducting. But for the reverse bias, how was it? There was a barrier electric field here, which was avoiding the majority majority carrier to pass, but actually that barrier uh, electric field could pass the minority carriers, right? So so let's say you have this barrier field, right? Built-in field, this direction, but this direction actually it can pass the minority carrier like holes of this section because the n-type also has some very limited holes, right? These holes can pass through this electric field, and the electron of this region also will easily pass through the other side, right? But since the number of the minority carriers is less, so it is not too much or huge current, right? So basically, we are using the same phenomena here to use it for the bipolar, right? So if you just put two junctions diode as a model of the transistor here, basically, let's say you have this condition, you have the base emitter diode is turned on, and then you have the other junction turns off, right? The D2 basically is reverse biased in this condition, right? Basically, it's two junctions, right? D1 is on. From this circuit, I mean from the schematic, based on the two diodes, you cannot expect that the I2 actually, you expect that I2 is zero, right? Because you are saying that the D2 is off and only I1 is on, so there is no pass from the VCE to go through the, right? But in fact, transistor is a little bit different. In the transistor, basically, you are biasing the forward bias, the base and emitter, right? So The emitter region is heavily doped, so that's why we put the N plus, means that this side is full of the electrons, and you are trying to turn it on, right? This the first junction. So these electrons, once you turn on the bias, the base emitter, actually these electrons can basically moves from this high density to the P region, right? But on the other hand, this other region is reverse biased. Reverse biased. There is a depletion region and there is a strong electric field here. So this electron, instead of going back to this side, basically absorbed by this electric high strength electric field, and then just as a minority carrier, basically pass through this side. That's how the transistor works, basically. It's, in fact, this electron moves to the whole region once you turn on this diode, and the electrons basically are the minority carriers for this P region, right? They are not the majority carriers. Once they reach here, it's like the minority carriers, and then the reverse bias region can pass the minority carriers. And that's how this works, right? So that's why they call it the collector. The collector basically is collecting, right? The collecting the minority carriers of this region. The P region is collecting, and this we call it emitter. This emitter basically has so many electrons because it's heavily doped, emit the electrons through this P region first. And once the electron reach to the P regions, it looks like they are like the minority carrier for the P, right? And then the minority carriers can be collected by that electric field of the reverse bias diode. Okay, so basically the collector current is similar to the diode equations. Why is similar? Because basically this electrons that is coming from here to here is initially for this turn on diode. So the electrons is reaching here basically is based on this VBE of here, right? It's similar to a PN junction. The current suppose comes out from this node, but it will be collected by the collectors, right? It cannot reach back to the base. So eventually the collector current formula is pretty much similar to diode, but instead with another, let's say with the third terminal that controls the output current. And this IS is depending on the area of the device, area of the emitter, the charge of the electron, the diffusion coefficient of the uh, electron, and the number of intrinsic carriers, the width of the base, all of the physical structure, and the number of doping especially, right? So, let's see what we want to say more. So basically, what currently we figure out is that the transistor, you can model it like a, using a current source, basically, right? From the collector to the emitter, if the emitter is ground. And then this current source basically can be controlled, the amount of current can be controlled by the input voltage of the base emitter, right? So this situation is valid once the transistor, we call it in a forward active region. Forward active region means that if the base emitter diode is forward bias and the other one is in a reverse bias, right? But this situation is valid only until certain region, basically. Here is showing is at least valid up to V1. V1 is what means that this voltage also is V1. If this voltage is V1 and base is V1, then the other diode basically is still turned off, right? This diode is turned off. We want active region is at in this region. This diode is off, right? And then the other characteristic for the transistor, basically, we need to know is that the base current, because the base also is a forward bias junction, right? As we saw it. The forward bias junction basically can carry some current, right? So the amount of the current carried by the base basically has some relation to the output current and is a beta factor. So it means that whatever output current you have, basically the base current is 1 over beta times less than the output current. So the higher the beta, the less input current for the base, right? And for the ideal transistor, we pretty much like to have much less current at the base, right? We really want to control the output current just like with a voltage, not drawing any current, right? So the better transistor actually has a higher beta, right? And at the end, the transistor, you can model it with this kind of things. Basically, it has some base current, IB, the base current, which is beta times less than IC, right? And then the emitter current basically is the sum of the IB and IC, right? The emitter current is IC plus IB, right? The two currents will be combined, right? And the IC, as we mentioned, basically is based on the diode basically equation, similar to the diode equation. If you combine, you can also write the current for the base current, just scale it, right? And then the IE, you can combine all of these things. We sometimes define another value, which is called this alpha. Instead of using this term, you can put this alpha here. So let's see a little bit more about the bipolar large signal model. So here is trying to model the transistor. Basically, it is saying that there is a base emitter diode here, right? Which the current voltage for the base diode is like this. And we know that the output current basically is also like a diode, but beta times of the base current, right? So here is trying to show what is the other limit we may face, basically. So let's say we are sweeping the value of the RC, right? I mean, this is RC. This is RC, right? Let's say the VBE is a fixed voltage, right? What will happen once the VBE is fixed? Let's say the VBE is a fixed voltage. How is the IC? Do you have an idea? Right? It is a current source, right? A fixed current source. Basically, then it looks like we put a fixed current source here and then we connected it to some RC and to a bias voltage, right? Then we want to see the Vx or the collector voltage is how. If the RC is 0, what would be the Vx? Let's say RC is 0. It's 2 volt, right? Because you're basically connecting directly the VCC supply just to the Vx, right? And once you increase this RC, basically what is happening? There is a fixed current passing by, right? So there is IR drop always, voltage drop. So it starts from 2 volt, but it drops based on the value of the resistor and the value of the current, right? Until reaching how much we can continue. If we, let's say, increase the voltage, the resistance, it should be 0 and becomes a negative even. Is it possible to do so? If we increase the resistor too much, right? And if we assume that this is a constant current source, right? The Vx is going down, reach 0, and even can go negative, right? If this is really a current source, is that possible? Let's give an example, right? Let's say this is 2 volt, right? This current source is 1 milliamp, right? And then you put the RC value of 10K kilo ohm. So what would be the value of Vx in this situation? How much is the voltage drop at the resistor, at the 10K resistor? 10 volt, right? Because the current is 1 milliamp, right? And how much would be this Vx then? Let's say here is the Vx, right? Minus 8, right? 2 minus 10 minus 8, right? So what will happen, let's say, in the transistor, if here this collector voltage becomes minus 8? Basically, you have the transistor, right? You had some VBE, let's say 0.8 volt, for example, right? 0.8 volt. And now you put the situation that this collector voltage is like negative 8 volt. What will happen? So the transistor, if you is kind of like two diodes, basically, right? We are saying the transistor is like a current source at which condition? At, at the condition of the VBE, basically, right? VBE is forward bias, but the other one is the reverse bias, right? But now, how is the situation? Now the collector is negative 8 volt, right? The base voltage is 0.8 volt. Is this diode forward or reverse? Is it reverse or forward? It's forward now, right? It's not valid then. The situation is not valid. We are assuming that this transistor is like a current source, right? But this is not the situation that the transistor is current source, basically, right? So, so what do you expect that this voltage can be then? It's close to 0, right? Because this is forward bias, so you have 0.8 volt at the base, and this one is turned on, so here is something around 0, right? 1 VDE on less than this voltage here, right? Is it clear? So then it means that once you are increasing this collector resistor, basically, the collector voltages start dropping, right? But at the max, it may reach up to 0 volt, right? From here. But in fact, in the device, actually, it cannot even reach 0 because the VDE on of the two junction are different. So let's say if this one is 8.8, basically, the VBE on, the other one is maybe 0.6. It's usually less. So this usually will be saturated up to something around 0.2 volt, right? So in fact, once we characterize the transistor, we tell that, let's say the VBE on is like 0.7 or 0.8 volt, right? In our characterization. And we give this VCE sat basically is something around 0.2 or 0.3 or 0.1, right? To show how good the transistor is, right? So this is important. We should first make sure that these assumptions are valid, right? You start with the current source initially, right? Because you are assuming that the transistor is in active region. But after solving, you will figure out whether this transistor region it was valid or not. If not valid, you need to update, right? So the so here also is showing the collector current versus the collector emitter voltage, basically, right? Which is a constant because it looks like a current source, right? The current is fixed. It doesn't matter of the VCE, at least at certain level. And then the value of the current source is actually adjusted by the VBE, right? You're using the base emitter voltage, you control the amount of the output current, right? And it's almost constant, like a current source, until VCE is larger than something. If goes to very close to 0, then it will be like 0, right? So for the transistors, we moving a little bit to the small signal region of the device. Let's say the transistor is biased at certain point, and then we want to slightly change the VBE and see how much current of the output current changes. This parameter is important to us because it's kind of showing how much gain basically the device has, right? Once you slightly change the input, how much the output current changes, right? This is the transconductance of the device. We show it with the GM. Since it's the transconductance, we show with G, right? The resistors, we use R. For the for the conductance, we use G, right? So GM means that how much current will change basically once the input voltage varies. And you need to take a derivation of the equation to basically because it's small change. And then you will come up the GM of this, right? It means if you, for example, change the base emitter voltage by 0.2, 0.1 volt, the output current changes this much, right? IC over VT, GM times of this voltage, right? So, so there is one thing more for the transistor we need to know it, which called the early effect illustration here mentioned. So you remember that we told that the output current of the device basically is constant over VCE, right? Which is pretty much like a very ideal current source, right? But in practice, actually, once you change the VCE, it is not perfectly constant. Slightly changed, right? So in some of the application, we also need to really care about this much of variation, right? Our initial assumption was a very good ideal current source. But if you want to be a little bit more accurate, basically, once you change the VCE, basically the output current changed, but not too much, right? So a more accurate model, instead of using the constant current source, basically, right? The initial term was a constant current source, which only depends on the V1. V1 is the base emitter. Now we are adding this term, which is showing that actually the output current also a little bit depends on the X voltage or the collector emitter voltage, right? If it is really a constant current source, the value of the current doesn't change once you change the voltage across it, right? It's always constant. No matter if this is 0 volt or 10 volt or something, right? It's always, let's say, 1 amp, right? But for the actual device, for this actual device, it tend to be like this, but it's a little bit changed once you really change the voltage of it. It looks like a current source, but once you have 0 volt, let's say is 1 amp, but once you go to 10 volt, it will be like 1.1 amp. It is increasing a little bit, right? So this is a more accurate model, and this constant here, this is a constant value for a specific transistor is a constant value. We call it V early, and this is some constant. It's usually fixed and like a very big number, like 100 volts. The value is like 100 volt. So it means what? It means this term means what? It means this is a big number. It means for example, if the VCE becomes like 100 volt, then the current will be double, right? The current from the ideal current source will change to something. The value of the current will be double. But normally the operation voltage of the device is much less than this value. Let's say we are going to work like with 5 volt, not more than. So it means that that the amount of the change is not too high, right? So again, this is the more completed large signal model. You have some input diode, right? You have this kind of current source that will be controlled with both of the input voltage, basically, and a little bit depends on the VCE, right? And then we can actually make the small signal model for the transistor if from this large signal model, basically, right? Basically, you have the diode here. The diode, we mentioned that you can model it with in a small signal with a resistor once it is forward biased, right? We are just putting one by one. We know that this current source basically is depending on the input voltage, the VBE. So, but the value of the change, the small signal, we calculated by GM, right? And the GM was what? GM was the bias IC, the bias of the transistor over VT, right? And then to show that the output current also changed with the collector voltage, basically, we can model it with another resistor here called RO, output resistance of the device, right? And then the RO is depending on this V early value, can be calculated by this formula, right? Right. So let's give some example. For example, if you bias your collector current with 1 milliamp, and the V early is 100 ohm, 100 volt, then this RO that shows how much the current changes is kind of what, right? It's a very big resistor, right? So basically means it will change a little bit of the collector current, like paralleling 100 kilo ohm resistor, right? So here is a little bit describing why the early is working like that. Want to go that through that thing too much. And here is also showing when the transistor basically goes to the saturation. So saturation means what? That's not T. BCE. Saturation means what? We are assuming that the collector is constant, right? Almost once the VCE changes, right? This region is the wanted region because we want to have the controlling the output current, right? It's active, forward active region, we call it. But once the VCE drops, basically, this region basically is what VBE is at which condition? The active region is how the VBE is forward bias, right? The other diode is what? Is reverse, right? So let's just load it again. The active region, basically, you have two. I'm just showing the diodes, internal diodes, basically, right? The active region, the first diode, the base emitter diode is turned on, but this one is in a reverse or turned off. Has to be, right? And we mentioned that once this voltage collector emitter drops going down, then there is a point that this diode turns on, the top diode. And then at that region, we tell that the transistor is in the saturation, right? So if the VCE becomes lower than something, then the current source is not valid approximation anymore, right? And on the other hand, you can tell that the beta, which is the gain, current gain between the IB and IC, also not valid, right? So if you remember, the IC was beta times of the IB, right? But once the transistor goes to the saturation, the collector current basically is reducing, right? From the actual current source, right? The current of the device, basically output current is reducing. And then if you want to tell in another way, the base current still is there, right? Because you are already forward biased the base current is always the same value. But the current of the collector is dropping once the VC is going to the saturation. So basically the beta effectively is dropping at the saturation. The beta is the ratio of the I out to the I base, right? Okay. So here again showing that things. Here showing that at the active forward active region, this diode basically is reverse, right? Polarity is like this, reverse. And in the saturation, this diode is turning on, which should not, right? Okay. So here is trying to say what is the acceptable VCC range or the collector range, basically, that the device still is like a current source. And here is saying that this acceptable VCE basically, I mean, this junction has to be like 400 millivolts less than VBE. It is saying that um, the collector voltage, basically, V collector, should be larger than the base voltage minus zero point 0.4 volt. What it's saying. It means that diode is not turned on very sharply. It's slightly before the turn on point. Still acceptable as the current source. And in the deep saturation, usually we can model the device easily with just two forwarded bias diodes, basically, which in fact will be like this. 800 millivolt for the base emitter junction, and the collector emitter is saturated almost to a fixed constant voltage of like 0.2 volt. These are useful once the transistor goes to the saturation. You just put it this model, right? We don't need to consider the extra things. On the other hand, we have the PNP transistors, right? I'm not going to too much describe about it. It's just everything is similar to the NPN, right? Just the direction of the current and the polarity change, right? Everything else is similar, right? The symbol basically is like this, right? Comparing to the NPN, right? NPN was like this. NPN was how? Here was P dope, here was N, and here was P. So the forward, sorry, this is PNP. Um, NPN. NPN, right? Since this PN junction was forward at this direction, we put this arrow like this, right? For the PNP, basically, we have P and P, right? But the polarity of the PN junction for the base emitter basically is this direction, right? So we put that arrow like this, right? And then again, we need to have all of the situations similar to the other one. Let's say we need to turn on the VBE, right? So we need to apply the bias voltage like reverse comparing to the NPN, right? Because the diode to become forward bias, the emitter voltage should be higher than base voltage, right? The NPN was reverse, right? The base should be larger than the emitter. And then you should make sure that the collector base is also reverse biased. So in order to make it reverse bias, basically the collector voltage should be less than the base voltage, right? Because this is N, this is P. You want this diode, the diode is like this, right? PN. You want this diode to become reverse bias. So if you have the base voltage, the collector should be less than the base voltage, right? So everything is pretty much similar to the NPN, just the direction of the current change and the polarity of the voltage, right? So here just comparing. If you have the NPN device and you have this VCC like the supply like this, then your emitter is at the lower for the NPN, the emitter is the lowest voltage usually, right? Because the base should be larger and then the collector also should be larger than the base to become this one to become forward bias should be larger than this, and this one to become reverse bias, this should be larger than this, right? VC larger than VB, right? And the VB larger than the VE, right? And then if you want to use the same thing with the PNP, basically, then everything is just reverse. V is the highest, emitter voltage is highest, then VEB basically should be positive. So V is higher than VB, right? To turn on this junction, the base emitter junction. And then to make this uh, base collector junction reverse, then the VC basically should be less than VB. So if you use the PNP, your load will be like here at the collector. If you use the NPN, your load is here. And the difference is this transistor drawing current from this direction, but the collector of the PNP basically is pushing the current to this direction, right? It's just a matter of the direction of the current source. So the NPN device, you cannot make the current that it always draw current basically, right? It always draw current toward the device as a current source. But for the PNP, it pushes the current out, right? So everything else is similar. That equation of the collector and base, everything is similar, but you see the polarity of the voltage change instead of VBE is VEB basically, right? And instead of VCE is VEC, still has that early effect uh, problem. And then this is again trying to show how we can draw the large signal model for it. Is a forward bias and one current source, right? And this is again showing how it is biased again. The lower voltage is for the collector, the higher voltage is for the emitter, right? Okay. And then let's see how is the small signal for the PNP. So for the small signal, again, you can put every part of the device, let's say. So is that the two things are similar, just showing in a different way, right? This is the transistor here. You put the diode with the pi resistor as a model of the small signal, right? One resistor. You can put the I out variation with some resistor and you have the GM, right? And if you see, these two models are pretty much similar. I mean, with the NPN and PNP. So the small signal model of the two devices are exactly same. Even doesn't have any direction in fact. So both are pretty much similar, right? So let's let me talk about how we actually need to plot this small signal model usually, right? For the small signal, what we need to do basically is you have let's go back again. I just a little bit describe this. So the transistor, we know that this is a current source, right? Can have some output resistance and is GM. This is the collector. This is the emitter. This is the base. And this is the VBE. And then the output is GM times VBE, basically, for the small signal model, right? But once you are going to put the small signal model in the circuit, basically, this is the full circuit, right? Then for the small signal model, actually, you are assuming that all the DC values are zero, right? So that's why you are seeing that for the small signal model, actually, the RC is grounded. Why we do that? Because for the small signal, actually, we are thinking that some small change is at the input, right? So it is not supposed it is not supposed that the like VCC change, right? We are just caring about those voltage or current that is changing. The others that are not changed, actually you can assume that there are no change, zero, right? Or if you have some current source somewhere, some DC current source, let's say you have this transistor, right? You have biased it with some current source, fixed current source, and from top is some resistance, some bias voltage, right? Like VCC. And then you are applying your AC signal basically here, right? Then how would be the small signal for this circuit? So what we are varying is actually this input, right? We keep it, right? The base basically, uh, the base has some R pi resistance, which is the diode resistor, right? Emitter is here. Emitter is connected to a fixed constant current source. What should we put it here for the small signal model? Sure. Is open, right? Right, because the current up here is not changing. So it's like open. If you put short, then the current can change, right? And then you have this GMV pi of the transistor, and then you have the RO of the transistor again, right? And then you have the RC, let's say collector resistor here. And then the other side of the RC is what? Is zero, because the VCC suppose not changing. Actually, you can tell that we are basically doing the superposition. We're assuming a linear region. So we are not going to find the response for the VCC and these constants. We want just see the response to the variation. So you're assuming this as a superposition, you're assuming this is zero, this is open, right? Because you don't care about it. You are just trying to find the variation of the input and output. Those who are not varying, basically, they are not doing anything. They are just short for the voltage source and the open for the current source. So now what has happened for this circuit is basically the small signal model is like this, right? So if we assume that here is the output voltage that we are looking for, and here is the V in, right? What is the output voltage in terms of the V in? Can you tell? Do you have any idea how it would be? So let me a little bit simplify this. Let's ignore this R out so then solve this circuit. Let's try to solve it. Versus input.
Should we knock this one? Should we take a loop?
Yeah. Just a loop, right? Single loop.
Single
Right.
loop.
Let's write it. Just a single.
I wrote this one, so you tell me.
Let's find the current
And
V pi is the voltage across the resistor.
so is it same as Vn?
Oh, right. We need to solve it to find it.
So V plus right? This one. Was it
Rotating back.
yeah, I'm checking this one. RC multiple of this current, right?
Yes.
Plus V pi. Plus V.
But V pi, you can also know what it is, right? It's basically Gm times R pi.
Plus Gm plus. Yes.
Right?
This is R pi, right?
This is R pi.
Is Gm V pi R pi plus Vn?
Gm V pi
R pi
R pi
plus V.
plus V in equal to what?
Vn.
So I can solve it with a little bit of more easier and tricky, actually. So we don't need maybe to solve all, but let's say you have the V pi here, right, across this resistor, right? If you have the V pi across this resistor, what is this I value? Let's say you have some V pi, right? What is the I, right? Is V pi over R pi. That's right. And then this current is coming this side, right? And then you have another current source here. What is the value of that current source?
-ohms.
Right? So on the other hand, you have the GM V pi coming from the other side, right? They are actually fighting each other, right? Then what does it mean in practice?
Equal but with a negative sign. Opposite.
But the direction already fixed, because if you have the V pi at this direction that I am writing, right, then the current of the base basically is this direction, right? And then the current of the other circuit also at this direction, right? So how this could happen? And there is nowhere else that these two current goes, right? Basically the IB, right, is coming from this side, and the IC is coming from the other side. They should be zero, right? There is nowhere to go. Is it clear? And then what will happen? Basically, the IB is this, VP over R pi. The other one is GMV pi, right? The sum is zero, right? Then what does it mean? Right, the equation is this: V pi over R pi plus GM times V pi equal to zero,
V pi equal.
right? Yeah, exactly right. This only can possible once the V pi is zero. And then what will happen if the V pi is zero? No current, right? No current. And then how is the output voltage?
To V in.
Is it V in? How can you say? So there is no current at the R pi, right? So here emitter is basically is V in, right? Because no current through the resistor, so no voltage on the resistor, so V emitter is actually V in. Is that correct?
Yes.
So how about the collector? If here is V in, how is the collector?
Same should be same, right?
Why should be same? You should be how is same? I mean, if it is same, how? I mean, here we have some current source, right? And the current source basically is kind of open, right? Because the V pi is zero, right? So basically we don't have anything there, right? Then V out is what? V out is only a resistor connected to the ground, right?
Zero.
Is zero, right? Is it clear?
Yes. Yes.
So in fact, if you bias your transistor using this current source like here, it cannot provide you any gain, right? But the situation was a little bit different if we had this R out. If we had this R out, it's, the problem was a little bit more complex because there might be some current passing through this resistor to the output, but it is not too much, I mean, practice, because this RO is very big and pretty much similar to what we solved. The result should be not too big. So then you remember again, for the small signal model, actually, we just uh, make the other sources zero, right? The constant source, we make it zero. Zero means short for the voltage source, means open for the current source, right? And then here again, showing the same thing for the PMP, right? The small signal models, if you plot it, is pretty much similar to the NPN. So from the small signal model, you cannot tell that the transistor is NPN or PNP, right? If I give you some small signal model of a transistor, you cannot know whether this transistor was NPN or PNP. Do you remember? It's only in terms of the bias and the direction of the current for the DCs are more important. So here's another example for the small signal model, which is still easy. So this is another small signal model. Can you try to plot the small signal model for this circuit? Oh, can you see how we exchange each transistor with the small signal model over here? Right? This is the Q1, right? This is the Q1, right? The base is connected to Vin, right? There is a VBE junction here. You put it this R, right? And then you have the collector current source and maybe this R out that's showing the variation of the collector current. And then you have this RC1 basically. RC1 from the collector is going to where? To VCC, right? You are assuming that VCC is ground for the small signal. So that's input is like this, right? And the other hand, this collector also connected to the emitter of the other device, right? Right? Is this correct? Do you think this is correct or not? The first part, it looks okay. The Q1, right? How about the Q2? The collector of the Q1 is connected to emitter of the Q2. Is this correct or it looks not correct for me? Here, right? So
It's correct, right?
is it correct or not? This collector basically is connected to the emitter of the Q2, right? You are saying that the emitter of the Q2 is connected to the collector of the Q1, right?
Again, Richard.
So
See the second figure on the right.
this, I mean this, so this is also similar, right? The collector of the Q1 is connected to the emitter of the Q2. So basically the two circuits have the same, they have the same small signal model. But this small signal model over here, I'm seeing some problem. Is there any problem? Can you, is there any problem or not? So can you plot for yourself? Can you plot it for yourself? I think it is not correct.
So this structure, this one. This is NPN junction.
Yeah.
This is PNP.
Yes.
And this one. Is it
Emitter.
not collector?
No, it's emitter. So he's trying to say that this slide is saying that these two circuits, in terms of the small signal, are similar because the collector of this is connected to emitter of the other. But in terms of the biasing and the bias direction of the device, actually different, right?
Therefore, it's not correct.
But what is the correct version of the small signal model for this?
Oh, there was anything.
And can helps to modify it. You find some.
Yeah.
And can you draw the correct version? Can you? So can you try to make the small signal model for this? Okay. So for the small signal model, each transistor has some small signal model, right? You need to just swap each transistors with the small signal model, and the VCC will be short.
This should be connected to this one, right?
Yes,
This point.
exactly. Right. Did you find a problem?
should in the second picture, the collector of Q1 is connected to the collector Q2.
That
But
the small signal model of what it's showing here is actually the collector of the Q1 is connected to each.
Emitter.
No, I mean the small signal is showing what?
Small signal.
The small signal is showing what?
Emitter.
The collector is connected to which port?
yes,
Base, right?
Yes.
It is showing that the collector is connected to the base, but in fact, that circuit is collector connected to emitter, right?
Yeah.
So the connection basically is wrong, right? Basically, the correct connection should be from this collector should be connected to here, right? To the emitter. Should be connected to the emitter. And then we should not have this ground here, right? How about the base? I mean, the base of the transistor is how? So I just, right? The base is ground. The base is grounded, right? The base is grounded. The collector basically comes to here. Base is grounded, and then the other things are okay, right? Yeah. So for our analysis, basically, especially for the analog and amplifier, right? First of all, we need some device that is in the active region. The active region, you can control the output current, right? Versus the input voltage, right? In the saturation, you do not have that much of control. Everything is just like a current, like a constant voltage source, right? And then once you have the transistor in the active region, you need to swap each transistor with the small signal model to be able to analyze it. This is the what we need to do for designing the amplifiers and analog circuits, right? And then after a while, actually, you do not need to really draw all of this bulky expanded version, right? You just, once you put the transistor, you already assume that there is some small resistor from the base to emitter, right? Which is R pi, and the R pi is, the value is depending on the operation point of the device, uh, VT over IC times beta, right? These are some formula you need to remember. There is some current source, right? Here, which depends on the VBE. The value is GM times VBE, right? You just put this. And in one level more advanced, you add the output resistors also here. The value is V early divided by the IC. The GM is also VT, sorry, IC over VT, right? So you do not need to re-expand it after a while. You just put it here and then it become straightforward if you do enough practice. So after this part, actually, we move on to chapter 5, which is more specifically, we consider the bipolar amplifier designs, right? So for the amplifiers, basically, we are defining some general concepts. The first thing or the basic things are like the biasing, like why the biasing important? Is saying what? Biasing saying that the transistor is at which region, right? Right? Is it saturated or is it active? It has to be an active if we want to make the amplifiers, right? And then what else is important for us in the biasing? We need to define the value of the IC, the collector current. Why this is also important? Because the small signal parameter also change with this IC current. The GM of the device is depending IC. The R out also depends on the IC. The R pi is depend on IC, right? So once you adjust this IC value, basically you're adjusting the parameters of the small signal circuit, right? So the bias is important. And we define what is the input output impedances of the amplifier, right? And then we can actually analyze the small signal and DC. So to bias the transistor, we need to provide some circuit, right? How you fix the design for a special IC value. You have the transistor, but how you bias it? You want this transistor to have special IC level, right? You need to provide some extra components to make sure that this IC is what you want. So for example, as you saw, if I just bias this circuit using a constant current source, let's say we have it somewhere, right? I can fix this IC, let's say exactly 1 milliamp by this current source here, right? Because the collector current basically is same as the emitter current, almost. Actually, the emitter current is IC plus IB, if you want to be more accurate, right? Some part of IC comes here, some part of IB comes here, and they combine, right? Makes the IE, emitter current. If I put a constant current source here, basically, I can pretty much define the IC because IB is already 1 over beta of IC, right? If the beta is large enough, you can tell that if I put something like IE here, then I am defining the IC very well, right? But you saw that in that example, if I put the IE here, basically there is no gain, right? I mean, the type of bias also important, right? This is one way to bias this transistor accurately. But if I use this type of bias, there is no gain for the device. We already saw that, right? We have different type of amplifier topologies, common emitter, common base, and common collector or emitter follower, right? We will go through this. So let's start a little bit of this, and then we will close this session. So here is saying, showing some voltage amplifier. Let's say we want to drive like the speaker, right? We have the microphone. The microphone generates some audio signal in the electric domain, right? Converts the, let's say, audio waves to the electrical format, right? You want to amplify it to be able to drive some louder speaker, right? The speaker has some impedance by itself, right? The speaker is like a load as I mean from the electric perspective, right? The microphone also generates a signal once you talk to it, right? But it looks like a source can generate something, but it also has some impedance, right? It's not like a very pure voltage source. It's like a Thevenin model, let's say. It's a voltage source plus some resistor or something, some impedance. So everything is not just ideal, right? It's not a very good ideal voltage source. It has some resistance. The speaker also is kind of some load. It is not open. It is drawing some current, right? And then you have your amplifier, voltage amplifier here. You try to put it, but your voltage amplifier at the input also has some input impedance, right? You wish that the input impedance to be higher or infinity in practice, but in fact, it has some limited value. So why do we need, in this case, that the input impedance of the amplifier we wish to have an infinite value?
To prevent the flow of current inside the input.
Yes, because the amplifier basically amplifies this voltage across it, right? V1, right? Let's say if the gain is 10, it amplifies V1 times 10, right? So we can go to the extreme case. What if this R in was short, like very low impedance,
Zero.
right? It was 0. And once you put the microphone inside, microphone has 200 ohm series resistor. So how much of the voltage generated by the microphone could appear at the V1 if it was short? Nothing, right? If the R in is like 200 ohm, what will happen? How much of the signal generated by a microphone actually comes at the input port? It, the resistance of the microphone is 200 ohm, and let's say the input impedance of the amplifier also 200 ohm.
Same.
Half of the
Half.
half of the input, right, is the voltage divider, right? So half of the input voltage is just dropping on the V1, right? And then the final amplification was how much? You wish to have 10 times amplification, right? Here, right? Initially. But because of this output, the impedance of the microphone and the input impedance of the amplifier, you are wasting half of the input signal, 10 times 10, right? Let's say the other thing is correct. Then so far the gain dropped to 5, right? So this we call the loading effect, right? The components, when they are in series, they are loading each other. So your amplifier is loading basically your microphone, right? It tries to draw current, and since this microphone cannot provide enough current because of the output impedance of itself, then the voltage reached to the input pin of the amplifier drops, and then the gain is less than what you expect, right? So then, as the amplifier designer, actually, you prefer to design some amplifier that the input impedance is higher, right? If the input impedance was like 200 kilo, then you don't care how much the almost whole of the V in comes inside the amplifier, right? There is not much drop because of the impedance divider. So on the other hand, this amplifier has some output, right? The output, you can model it with some voltage in series with some output resistance, right? Nothing is ideal again, right? Your amplifier may generate very large gain, but it also has some output resistance. So if you don't have any load, basically, the output is really large, right? Because there is no drop across this output resistance. Whatever the amplifier generates as the voltage, you can see the very large voltage here if there is no load, right? But what if you really connect to a speaker? The speaker is like 8 ohm resistant, right? And what if your amplifier output resistance is also 8 ohm? You expect what? You expect that this amplifier is generating 10 times of the input signal, 10x. But once you connect the 8 ohm to the output of this amplifier, actually, the final reached voltage to the load is again half because the output impedance of your device also 8. So half of the voltage is wasted, right? You wish to get 10x again because of the output resistance is not too low. There is another voltage divider at the output side. right? Then what you ideally prefer is that this output impedance to be very low or zero, so that whatever load you put, it really gives that voltage, right? If the output resistance was zero, then whatever it amplifies, it reached to the load, right? So then for the voltage amplifier, basically what we prefer is the input impedance to be very high, right? Infinity. The output impedance to be low, zero, right? But in practice, it's difficult to reach these things, right? Nothing is ideal. Everything has some limited value, right? Reaching to zero and infinity, both sides are difficult. So tomorrow we will continue from here. All right. Tomorrow, I mean Monday, next session. So this is something that you need to also consider in the project we are going to solve, basically. Right? So do you have any questions so far?
Can we expect our certificate exam result?
Will be released soon, I guess. Yeah, I need to finish it. I guess finish it this week.
This week?
Maybe, yeah, I will finish it. It's not much left. Yeah,
For Sunday.
I think so. I think so.
Okay.
Yeah, I think so. Yeah, okay. So from now on, I guess it will be more practical again, a little bit less physical. We play with small signal and the biasing circuits. It should be more easy to understand, I guess. Okay. Anything else? Okay. Okay, then see you next week on Sunday, actually. Thank you so much for attending this session.